Give me 1 minute, I just quickly. Okay, so yesterday we talked about two-way slabs, and we talk about different panels, yeah, the corner panels, edge panels, and the interior panels. So we have different conditions. We may have different edge conditions, or it will change the panels. So when you have such a set of panels, it's very similar to your project as well. Okay, so generally the deflection is critical. Deflection is critical for a corner panel. Okay, for a corner panel, we'll have larger deflection normally. Okay, so if you have all the spans same as the interior and the exterior panels, so technically the corner panel become critical in terms of the deflection. Okay, so you consider the corner panel, and you have two spans. Okay, if you consider one panel, so corner panel, so LX and Y, LX and NY. So this one, you may have deflection in both direction, X and Y direction. Yeah. So generally use the shorter span. Use the shorter span for this one. Okay, you have to use the shorter span. For just such facilities. Okay. So you can use closed number closed number 9. So you have this equation, deflection at closed number 944. So this is the same equation you might use in the one-way slab or two-way slabs. Okay, one-way slab or two-way slab. This is the same equation. It is very similar to what you did in the beams. Yeah. So in beams you might have K1 and K2, and instead of 1000 you have B over there. Okay, B is the width of the beam, B is the width of the beam. So you might have similar inequality, but it is has some numbers different. Okay, so K1, K2 become K3. So that equation LE effective upon D should be less than or equal to K3, K4 delta upon L effective okay. So if you have such things, LE effective upon D, K3, K4. So in this case, you have K3, K4, all other parameters you should be able to know how to get it. So K3 and K4, you should be able to get from here. Okay. So for one-way slab, so for one-way slab or flat slab, the K3 values are there. Okay. For two-way slabs, you need to, for two-way slab, we will get everything from here. Okay. For two-way slab, rectangular slab supported on 4 sides, that is the two-way slab. So K3 should be 1 and K4 should be taken from this table. Okay. So depend on the edge condition, you should be able to get the K4 value from the table 9442. Okay. So you should be able to check your assumed depth. Okay. So you should be able to you check that one. So that is the first step in the slab design. Okay, that is the first step in the slab design. Then now you have the depth and all the things. So the step 2 is finding bending moment. I put shear force in the bracket because, as you know, we don't normally need to provide shear reinforcement in slabs. Okay, generally the slabs will satisfy with the VUC condition. Okay, no shear reinforcement required. So we only need to look at the bending moment in the most of the cases, but you also should be able to find out shear force diagrams. Okay, so for that, use the clause 6.10, clause 6.10. Clause 6.10. To get the bending moment and shear force for one-way slab, you use the same as continuous beam. So we did that one. So the same, you know that the ft ln squared upon some numbers. You remember this one? ft ln squared upon 16 or 9. So for different location is different numbers. Yeah. So you should be able to get that one using the same clause. That is for one-way slab. It is a two-way slab. So we have a little bit different approach. So if it is a two-way slab, we'll consider one panel. Okay, so this is Lx and Ly. Consider one panel. Then for Lx and Ly, the bending moments in both directions. Yeah. So this is mx star. This is my star. Okay. Mx, my, something like this. So these are the mid-span moments. Okay, mid-span. It is given in the standard, the same clause 6.10. If you go further, in the same clause, you will find these equations. Both are Lx squared, not Ly. Both are Lx squared. Okay, both are Lx squared. So that is given in 6.10. So the equations are given here. Okay, so these are the bending moment at mid-span. Okay, so Ft is the design load. Lx squared, you know, the shorter span. The beta x, beta y, you can get from the table 6.10.3.2. So that is this one. We'll use this table. We will use this table to get the beta x and beta y. So beta y is only one value for any Lx and Ly things, but the beta x will change. So if you know Ly and Lx, you should be able to find out beta x. Beta y is same for all Ly and Lx values. Okay, so we already discussed what this H condition means. We already know what this H condition means. Yeah, so one short edge discontinuous, one long edge discontinuous, two short edges are discontinuous. So we know those things already. Yeah, so we should be able to get the beta x and beta y. Ft is the design load. Ft is the design load. You should be able to find out mx and my. Okay, so this is a mid-span moment. Yeah, that is mid-span moment. At the mid-span, we have this much of moment. So we have something like this. Now I just draw only the mx, okay? We can do the same thing for my as well. So this is mx star. You already calculated, yeah? I only draw this one. So this is the mid span. So that's a moment at the mid span. So how can we do this one here and there? So what, because this is a support, okay, this is a mid span, this is support. So to get these moments, we need to multiply the mid-span moment by some numbers. The factors are given just below this equation. So if you read the standard, if you go further, it will tell. So this factor, so if it is a discontinuous edges and continuous edges, okay? So if it is a discontinuous edges, so if, let's say there is no slab here, there is no slab here, if there is no slab here, it's a discontinuous edge. If it is a discontinuous edge, then this mid-span moment should be multiplied by 0.5. Should be multiplied by 0.5. If it is a continuous edge, it should be multiplied by 1.33. Okay, so if you have something like this, we should be able to find out the support moments. Okay, so the bending moment diagram. So this is, let's say if it is a, both are continuous, both are 1.33. okay, it's depend, I just put as a discontinuous and continuous. It doesn't mean every times like that, but if it is a discontinuous edges, the factor is 0.5. So the bending moment diagram, 0.5 here, the mid span, the support. So if it is a 0.5, here 1.3. So your bending moment diagram, looks like this. Okay, similarly you can do for my in that direction. You should be able to draw the bending moment diagram. If it is a discontinuous edges, this is continuous edge, so then you get more like so. Now is always larger, x moment always larger than y moment, okay? Otherwise something wrong in the calculation or your directions, okay? So mx and my you should be able to calculate, and you get something like this. So now you have bending moment diagram. You should be able to find out, say for example, for mid span, what is the maximum bending moment? For support, what is the maximum bending moment? So you should be able to find out at support. We will provide strain force on the top and find the maximum moment, then find AST and check for minimum reinforcement, also check for spacing. Spacing cannot go more than that, okay? It cannot go more than this one. So you should be able to calculate AST, the reinforcement, okay, at the support, and same thing okay. So now we need to look at what is other things we need to look at, we need to do, okay? Any questions so far in the slab design? How to find out the depth of the slab, how to find out AST? Any questions? Any question from anyone? Okay, so then we don't need any shear reinforcement generally. So if you want, you can calculate the shear force. You can calculate the shear force. You can calculate the shear force the same way as you did in the beams, and normally this will satisfy. Okay, so V star, normally V star is less than or equal to pi VUC. So in that case, no shear reinforcement is required. We'll check for the crack control. The crack control calculations are same as we did in the beams. That's what we did in the tutorial 1. So we'll check that crack control. If it is interior slab, generally you don't need to do anything here. That spacing 300 or 2D should be sufficient. Okay. If it is interior slab, just checking for the maximum spacing and make sure it is less than 300 mil or 2D, whichever the lesser. In that case, it should be okay. Okay. So technically, we need only this much of calculation. Okay. This much of calculation. Someone is studying inside the car. Okay. So someone. Okay. Anyway, let's see. So now let's see what we need to do with the flat slab. Okay, the flat slabs are slightly different. I will complete the detailing everything together. But the flat slab. So what is flat slab? So when you have a slab technically you don't have any columns, sorry, any beams. Okay, this is a slab, you don't have any beams here, rather the slab is supported by columns directly. So it is not necessary you need to have columns in each and every place, but I just put some columns. So we have 20 columns. Okay, the side view, generally when you look at that this one, the slab, at the moment I just put as normal, okay, but sometimes we'll have a little bit different way. I'll talk about that one later. So the columns will take the slab, okay. So if you have something like that, the load distribution is a little bit tricky. So if you look at this panel, the load will go to the columns. Yeah, all the loads need to go to columns because there is no beams. Earlier, if you have beams, so we said it will go here, 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 but there is no beams then now. So if you don't have beams, what will happen? All the loads here will go to the columns. So the load transfer mechanism is a little bit different. Yeah, it is different. So the load will go to this column. So that's not, it is going this way and this way, both direction, but still it is not same as what we learned for two-way slabs. So in this case, what we do is we use strip method. We use the strip method, okay. I put that all these details there, but I just explain step by step what to do, okay. So strip method means you need to divide this column into strip, we divide this slab into columns. So what we do is we divide this one, say 1/2, okay, roughly, then further, so almost 1/4, okay. So we will divide into 1/4, half, quarter, quarter, okay. So if we put that one, so this one is called column strip. Here, this one, and this one also. So this is called column strip, column strip, column strip, column strip. Okay, and this one is called middle strip. Called middle strip. Okay, so this is roughly roughly 1/4. Okay, so center to center distance of the columns will be divided into 4 equal parts roughly. Okay, can go a little bit up and down, but if you divide by 1/4, it is good, easier. Okay, so this is for one direction. We need to do the same thing in the other direction. So this is column strips, and this is a middle strip for the other direction. Okay, so because we need to do it in both directions, the load can transfer in both directions. Okay, so you can see we have, if you look at this area or any area, we have, if you look at this one, so this one, this area, column strip, yeah? So we have column strip intersection, yeah? And this one, column strip, but this middle strip. So column strip and middle strip intersection, yeah? So this way it is a column strip, this way it is a middle strip. So this is CM. Okay, and if you look at this one, this is middle strip, this is a middle strip, so we have mm. So we may have three type of zones, yeah, CC, column to column strip and column strip intersection, column strip and middle strip intersection, middle and middle. Okay, so if you look at these three intersection, the column to column, normally it will be around the column area. Okay, so that is a more critical one. Large moments, large shear forces will act in that region. Okay, the next one, the M and M, this region will have very low bending moment, very low shear force. CM is between CC and MM. Okay, so we have three different zones and we need to design reinforcement for them. So what we can do, so the design approach. So I assume you have the loads, yeah, you know, step one, what is the first step? That is the same way, LE upon L effective upon, isn't it? D K3 K4 want the same inequality, yeah, so you should be able to check it. So I don't think that's any problem. The L effective, what is L effective? Minimum of ln plus d in L. L is the center to center distance, yeah, ln is the clear distance. So you should be able to find out effective length. So now the question is, what is the next step? We have two different strips, column strip and middle strip. Which one I should take? Which one I should take? So here the step 2, define the design strip. Okay, we need to define the design strip. So we have column strip and we have, this is the column strip, yeah, and the middle strip. So what we do is, I will just enlarge that one in case. Okay, we have a column here, we have another column here, okay, something like this. So I divide So what we do is, I will mark the half point here, center, and other half here. Okay. So this one is called design strip. So that means within the design strip, this is the design strip. So within that one we will have a column strip, we'll have a column strip, okay. So we have column strip, and half of the middle strip. This is a middle strip, yeah. So we have a half of the middle strip here and another half here. Okay, so if you look at that, show a diagram. So your design strip will look like this. Okay, the design strip will look like this. So we have column strip in the middle, half middle strip and half middle strip in both sides. So this is the design strip. I'm going to design steel and bending moment every calculation for this design strip. Okay. So the first step, we need to define the design strip. So that is LT. So this one is LT. Okay. So I'm going to, because what we did for one-way slab and two-way slab, we use 1 meter strip. Okay. Remember, that is a main difference in one-way or two-way slab. What we did, we take 1 meter strip, yeah, 1 meter strip, to do the calculations. Here it's not 1 meter because it's each location. So if you take 1 meter, is a little bit different from here. Yeah. So this 1 meter, this 1 meter strips, if you take from here or here or here, it is different. So we can't use 1 meter strip because it will be different for each location. So we use design strip. It will be more than 1 meter. Okay. So that design strip consists of a column strip in the middle, yeah, and 2 half middle strip. Okay. So now I am going to design this one. This is where normally many students confused. So the design strip is something like this, the thickness. In 1-way and 2-way slabs, we use 1 meter width. This is 1 meter. Okay. So now we have column, you may have another column, you may have another column, yeah. So we have somewhere here we have column strip, so this is a column strip and this is half middle, yeah. So these are column. So from now onwards, okay, so I am going to see from here. So if you see from here, what you will see? There is a column. And we have another column. And we have another column, something like this. Yeah. Yeah. So when you see from here, there is a column, column, column. So C1, C2, C3, and it will continue. Yeah. So I need to design this strip. So I need to find out bending moment first. Yeah. To design reinforcement, because I already decided the depth. Depth is okay. Now I need to design the reinforcement. If I need to design reinforcement, I need to find out the bending moment. Okay. So we use some different approaches for bending moment for 1-way and 2-way slabs. This one is a little bit different. So here, each span may be different. This one and this one, everything is different. Yeah. Everything is different. Maybe can be same. Okay. So we define total static moment, MO. This is FD, LT, okay. So this is given in close number 6, 10, 4, 2. This is total static moment. This is total static moment. So now for each span, okay, you need to calculate. So it is 6.4 6.42 or 10.42. So this is the section I'm talking about. Okay, here. So you should be able to find out so you know there's all these values. Okay, I'll come to that one in a minute. LO. So FT is the load, LT is the width of the design strip. Yeah, you already know. So for each span, so for this span, so this is span 1, span 2, span 3. For each span, we need to define MOs. So MO1, MO2, MO3. If the span is same, it will be same for everything. Okay, because only the LO is different. All others are same. LT is this one. This is the LT. This is the LT. Okay, LT is the width of the design strip. So if you have that one, FT is the load, FT is 1.2 G plus 1.5 Q, yeah, the design load. So LT also will not change, FT will not change for the whole spans, yeah, only the LO will change. So what is LO? So this is, say, L minus 0.7 of sigma A support. Okay. A supports. So what is A support? What is A support? So if you have at the end, so you have one span, yeah, this is one of the span, yeah. So A support is technically this one. will show the diagram. Yeah, but it is sometimes a little bit different also. Give me a second, I will just show the diagram. So generally this is a support, but sometimes we'll have some little bit different arrangements. Okay, so that here, so here we'll go, but here you may have some drop panels. So you may have some drop panels you might see in some of these structures. Yeah, you might see, I think if you show some diagrams. Yeah, so you might see here the drop panels. Yeah, so around the column you'll have some another square kind of things. Okay, so that's normally provided to reduce some punching here, so we'll talk about that one a little bit later, but you may have some different arrangement. So if you have something like this, okay, if you have something like this, what you need to do is from this line draw a 45 degree. Okay, so you draw a 45 degree where that meet at the center line. So this is a support. Okay, so this is given in this diagram 6-1, so you should be able to see. So they define here 614b. 614b explain how to get the A support for different conditions. Okay. Is that clear? So we will sorry, it should go. Should touch here. So if you have something like that, you should be able to find out MO for each span. If the span lengths are equal, you have same MO. Okay. So this is total static moment. This is the total static moment. Then we need to find out what is the moment here, here, here. Yeah. So because this is a total static moment, it doesn't mean moment somewhere else, somewhere along the string. So to find out the moment at support and the mid span, we use a table. So we'll go to table 610.4.3a or B. Six ten 4.3. So if you go to the table, just show that one. So here, so this is the table. So this is the distribution factors for the end span. End span is the end ones. All of the interior spans, table B. Okay, A for end span, B for interior span. So if you look at the table, this is for the end span, this is for interior span. So this is end span and this is interior span. So all others are interior spans, only the first one and the last one are the end span. Okay, first and last ones are the end spans, all others are interior spans. So let's see how to find out the bending moments. Okay, so I draw line diagram. Okay, just put the columns as with the line, easier. So this is end span, this is interior span, this is another end span. Okay, it is finished. So here we have MO1, MO2, MO3. Let's say we have different MOs. Okay, so you calculated MO values for each span. Then you go to this table A. So read this one. What is the condition? The flat slab with exterior edges are unrestrained. The flat slab with exterior edges are restrained by columns only. Flat slab with exterior edges restrained by beams and columns. The flat slab with exterior edges are fully restrained, and the beam and slab construction. Okay, so that's different. So what we did for the exterior edges. So what is exterior edges? What is exterior edges? So here. Okay, so when you look at this one, the big diagram, so this is called exterior edges. Okay, so in this case it is restrained by columns. Okay, so exterior edges are restrained by columns in this diagram. So if you have different cases, okay, so if you have we have columns, okay, so no beams. I just put the lines to draw the columns. The black dots are the columns. Okay, so exterior restrained by columns only. Okay, we have only columns. So if you have exterior edge, so let's say we don't put any columns here, so only columns are there. We have lots of columns, but not the outside. So we call this one exterior edges is unrestrained. Okay, like that we need to look at what is the condition we have for the exterior edge. Okay, so in our case, we said in our drawings earlier, the exterior edge is restrained by columns only, the second one. Okay, is it understand, or is not clear? So we look at the how the exterior edge is supported. Okay, whether you have columns along the exterior edges or you don't have any columns or beams in the exterior edge. So that is the first case, unrestrained. Or you might put beams around the exterior edges, so that is third one, beam and columns. Okay, so if you have something like this, we will decide which one is best fit for our case. Then if you have the second one, we have these three values. So exterior negative moment, positive moment, interior negative moment. Okay, so just look at the 0.25, 0.5, 0.75. So the first one is, so my case, this is the end span. They said exterior negative moment is 0.25. Exterior negative moment. This is the exterior one. This is exterior negative moment 0.25. So you just need to multiply the MO1 by that factor. The last column is interior negative moment 0.75. So interior for this end span, this is the interior, this is exterior. Okay, I'm talking about end span, exterior, interior. So this factor is 0.75 MO1. For positive, they said 0.5. So your bending moment diagram like this. Okay. Similarly, for exterior 0.25 MO3, for interior 0.75 MO3, for this one 0.5 MO3. So you will draw the bending moment diagram. So we have the bending moment diagram, so it should be a nice curve. So now we need to find out for the interior spans. For interior spans, it is the next table, 6, 10, 4, 3b. So here they don't worry about the flat system. Everything negative moment is 0.65, positive is 0.35. Okay, for everything, for interior span, negative moment means at support, mid span is 0.35. Okay, so if you look at that here, 0.65 MO2, here also 0.65 MO2, here 0.35 MO2. So your bending moment diagram looks like this. Okay, so this is how we develop a bending moment diagram for the design strip. For this entire strip, we have the bending moment diagram. Okay, so at the first support, this much. Okay, this is the end span, this is the end span, this is the end span, something like this. If it is the interior span, something like that. Okay, so if you have 5 or 6 interior spans, you have more and more spans there. Okay, but the factors are the important one. Okay, so now you have bending moment for the design strip. Any questions so far? Because the calculation is a little bit longer, the flat slab. Okay, any questions so far? It's still not finished. Okay, so we have the bending moment diagram. We should be able to draw the bending moment diagram for the design strip. So depend on number of span, we should be able to draw the design bending moment diagram. Yeah, so this is for one direction, for other direction also you have to do it. Okay, now the question is, okay, for example in this one, so if it is at support, you have some numbers here. So this moment is for the whole design strip. Yeah, do you think it is same for column strip and middle strip? So if it is 100 kilonewton here, do you think everything is same everywhere? It will be equally distributed? So if we say that bending moment diagram at the end support, you can find out the value. Yeah, so let's say this is 100 kilonewton. Okay, let's say this is 100 kilonewton. So do you think the 100 kilonewton bending moment will act uniformly across the cross section? It is not. We have two different strips here. We have column strip and middle strip. Yeah, so the total moment is 100 here, or if it is a mid span, somewhere here, you should be able to find out. So the bending moment will give some values for the whole design strip, but it is not uniformly distributed between column strip and the middle strip. Okay, so it's a little bit different because column strip will take more moment. So you calculated the total moment at each location along the strip. You calculated the total moment. You calculated the total moment along the design strip, but it is not uniformly distributed across the cross section. So we have column strip and the middle strip. Obviously, column strip will take more moment. Okay, column strip will take more moment. So if you have, let's say, 100 here, column strip may take 70 and the middle strip will take 15 here, 15 here, something like that. Okay, so how to distribute the total moment between the column strip and middle strip? That's the next question. So we calculated the bending moment for the design strip, and we need to, okay, so to do that there is another table. Okay, there is another table. If you go to that, so this is the table we use to distribute the moment to the column strip. Okay, so this table will tell you so how much the negative moment at the interior support, negative moment at the exterior support. So these are the support moment and the midspan moment. Okay, so we have negative moment in the interior support, we have negative moment at the exterior support. Okay, and this is the midspan moment. So if you have something like that for the strength limit, ultimate limit, so up to 60%, sorry, from 60 to 100% will go to the column strip. So normally we will take the average of that, 0.6 and 1, average is 0.8. Okay, so if you have a negative moment in the interior support, 80% will go to the column strip, 80%, so average of these two. Okay, so 80% will go to the column strip, other 20% will go to the middle strip. If it is negative moment at the exterior support, average is 87.5. So 87.5% will go to the column strip, the rest 12.5 will go to the middle strip. So that's how here it is, average is 0.6, so 60% will go to the column strip, 40% will go to the middle strip. So that's how we distribute the bending moment. We calculated bending moment, we calculated from this one. So if you have many, this one, we have the bending moment diagram. This is 0.25, 0.5, the factors. I just repeat that whatever I draw in the previous one, so just, you don't need to to explain, I just put some numbers, don't worry about it, I just put some numbers. So let's say 250 kilonewton meter, this is 500 kilonewton meter. Okay, to explain I just put some numbers. The red colors are just the numbers to explain. Everything is kilonewton meter. So this is the bending moment diagram for the design strip. Okay. I'll provide a full working solution for a flat slab. Okay, with this recording, when you look at that one, you will understand. So now the design strip means half M C half M. Yeah, middle strip, half of the middle strip, half of the middle strip. So if you look at this moment, this is end support. Yeah. So this moment they said, if you look at the table, if you look at the table 6.9.5.3, so we can find out bending moment diagram for column strip. So we will have the same arrangements. So they said negative moment, the first one, negative moment at the interior support. So this is the interior support, this is the interior support, this is the interior support. Okay, so these are the exterior support or end support, this one and this one. So interior supports are these. Okay, so they said in interior support, point 621, this much of, this is the factor for the column strip. Column strip will take 60 to 100% of the moment here. Okay, so since it is a range, normally we use the average value, which is 0.8. Okay, 80% of the moment of the design strip will go to here. So 80%, how much? 80% of 750. So 0.8 times 750, 600. So 80% of this one, 600 will come there. Here we have 650. Yeah. So 80% of the 650. 520. So this is 520 as well, because 80%, 80%, 80%, 80%, 600. So for all the interior supports, I have marked. For exterior support, they said it is between 0.75 to 1. Okay, so the average will be 0.875. So 87.5% of the exterior support. What is the exterior support moment? 250. So 250 times 0.875. So you will get 218.75. 218.75. Okay, and the mid span, they said it is between 0.5 and 0.7. All are in this table. Okay, so the factor average, it's 0.6. So 0.6 of the mid span here. Okay, 0.6 of the mid span, so that is 300. 500 times 0.6, then 0.6 times 350, 210, 210, 300. So the bending moment diagram, we have all the values. So this is the bending moment diagram for column strip. So then we will design for this moment. So we know the maximum moment at support, say 600. We know the column strip. So column strip, we'll take the column strip. Column strip is LT by 2, half of that. And you know the bending moment is, say, maximum is 600. So then you will provide the reinforcement on the top. For the 600 kilonewton meter, B is equal to LT upon 2. So you should be able to find out, the D is known. From that you should be able to find out small d, and you should be able to find out. So that is how normally we work out the area of steel for the flat slab. Okay, so as I will put these videos for that week 5. So you should be able to see all these calculations. I also put, because in the flat slab normally we'll have many other things, but most of the things are same as a slab thick, normal slabs. So the bending moment calculation is the more critical one. Okay, any questions? Okay, any other questions? Yeah, so as I told, I will put those details and I will talk to you in the after the break. Huh? So that's anything else?
One way and this one flat slab as well?
I'm not sure. I will check that. I will update all the things tomorrow. I don't. Yes, Monday and Tuesday a little bit busy. So, but tomorrow I will put the solution for one-way slab, two-way slab, and flat slab.
Okay, sir. Thank you, sir.
So one-way slab and beams are very similar anyway. But I put it everything. If you need anything further, just let me know.
Sir, can you upload the
Yeah, I will do that one. Yeah.
we file?
Yeah. So that's what it's not open yet. Yeah. Okay.
The assignment due date is week 7, yeah, sir?
Yeah, week 7. Yeah.
Sir, but we haven't learned the column design, sir.
The column week 6. Yeah, next week. So after the break.
Oh, after break, sir?
Yeah.
Okay, sir. I thought the week 6 is the break, so upcoming week will be week 7.
No.
Week 6.
So we have almost 3 weeks now, I think. From here.
Yeah, sir.
Okay.
Okay, sir. Thank you, sir.
Okay. So we will put that one and see how that will go. Okay. Yeah, I will update that one. So check all the things tomorrow afternoon. If anything more you need, just let me know. Okay.
Sure, sir.